Interference is such a fundamental aspect of waves that observing interference is proof that something is a wave. Since sound is a wave, we expect it to exhibit interference. One example of sound interference is that some type of headphones use the phenomena of constructive and destructive interference to cancel out outside noises. Although completely destructive interference is possible only under the simplest conditions, it is possible to reduce noise level by 30 dB or more using this technique. Suppose we hold a tuning fork near the end of a tube that is closed at the other end. It can be observed that the air column in the tube has only certain natural resonance frequencies, in which cases the incoming and reflected sound form a standing wave in the tube. For a tube closed at one end, since the motion is constrained at the closed end, no air displacement is observed at the closed end, and a maximum air displacement is observed at the open end. The maximum air displacement is called an antinode in the standing wave, and no displacement is called a node in the standing wave. The distance from a node to an antinode is 1/4 of a wavelength, so that this corresponds to the wavelength equals 4 times the length of the tube. Given that the maximum air displacement are possible at the open end and none at the closed end, there are other shorter wavelengths that can resonate in the tube, as shown in the picture here. The lowest resonant frequency is called the fundamental frequency, while all higher resonant frequencies are called overtones. All resonant frequencies of a tube closed at one end can be expressed as f sub n equals 2n minus 1 times the speed of sound over 4L, where n equals 1, 2, 3 corresponds to the first case, the second case, and third case. Another type of tube is one that is open at both ends. The air column in tubes open at both ends have the maximum air displacement at both ends, as shown in the picture here. All resonant frequencies of a tube open at both ends can be expressed as f sub n equals 2n times the speed of sound wave over 4L, or n times the speed of sound wave over 2L. Here n also equals 1, 2, 3 corresponds to the first case, the second case, which is the first overtone, and third case, which is the second overtone. Let's look at this example together. In the question, it says it's for a tube closed at one end, so that we have the fundamental frequency f1 equals the speed of sound wave over 4L, and the length of the tube is the speed of sound wave over 4F. Since we have at 22 degrees Celsius, the speed of sound wave is 331 times the T, which is 295 Kelvin, corresponds to 22 degrees Celsius over 273, and we get 344 meters per second. We plug in all the numbers and get the length of the tube should be 0.672 meters. For part B, the frequency of its fourth overtone is F5. Please note that's 5 here. Of course, the fundamental frequency is F1. So F5 equals 2 times 5 minus 1 and times the whole thing, and we get 1.15 kilohertz. We have learned that hearing is the perception of sound. Normal human hearing had the frequency range from 20 to 20,000 Hz. Sounds below 20 Hz are called infrasound, whereas those above 20,000 Hz are called ultrasound. Some animals, such as dogs, can hear sounds as high as 30,000 Hz. And other animals, such as elephants, can respond to frequencies below 20 Hz. Ultrasound, in particular, has a tremendous number of applications, especially in medical therapy and diagnosis. You may read Chapter 17.7 for more information about this part if you are interested. The perception of frequency is called pitch. Pitch perception is directly related to frequency and not greatly affected by other physical quantities, such as intensity. The perception of intensity is called loudness. Loudness is not only related to intensity itself. Frequency has a major effect on how loud a sound seems. Different instrument produces a distinctive set of frequencies and intensities, and we call our perception of these combinations of frequencies and intensities the timbre of the sound. A unit called a phon is used to express loudness numerically. Phons differ from decibels because the phon is a unit of loudness perception, whereas the decibel is the unit of physical intensity. This graph shows the relationship of loudness to intensity level and frequency for persons with normal hearing. If we know the frequency and intensity level of a sound, we can determine its loudness in phons using this graph. The hearing mechanism involves some interesting physics. The sound wave that impinges upon our ear is a pressure wave. The outer ear, or ear canal, carries sound to the eardrum. The middle ear converts sound into mechanical vibrations and applies these vibrations to the cochlea. The lever system of the middle ear takes the force exerted on the eardrum by sound pressure variations, amplifies it, and transmits it to the inner ear via the oval window, creating pressure waves in the cochlea approximately 40 times greater than those impinging on the eardrum. Two muscles in the middle ear protect the inner ear from very intense sounds. Pressure waves moving through the cochlea are converted into electrical nerve impulses sent to the brain. Hearing losses can occur because of problems in the middle ear or the inner ear. You may read more information about this part in the textbook.